All right, let's get started. So today we will conclude the chapter on traditional distributed database management systems. And we're gonna start discussing about another class of systems which make a couple of different design choices compared to traditional database systems. The last time we have already been discussing about how distributed database management systems differ from single site systems in terms of things like catalog management, query processing, concurrency control. This is where we have stopped last time. And next, we are going to discuss how we can recover data after one or multiple crashes in a distributed database management system. So first of all, recovery in a distributed system is complex. It is already complex for one single node. And here we can assume that the system is either running or not running. In a distributed system, we might have a situation where some subset of nodes has failed, but the other nodes, they continue processing. Also, now we don't only care about the nodes, but we also care about the communication between the different nodes. So there is a larger variety of possible problems in a distributed system. And in order to keep your data consistent, you have to take all of those special cases into account. So the protocol that we will discuss in the following, it's one of the most popular ones, that is the so-called two-phase commit protocol. This protocol essentially guarantees that distributed transactions that involve multiple sites are executed atomically. So it won't happen that some subset of nodes decides to proceed with a transaction while the other nodes decide to abort the transaction. So we make sure that all of our sites in the distributed database management system act consistently. In this protocol, you have two roles, the coordinator and the subordinate. So the coordinator is the site that controls the distributed execution of a transaction, while the subordinates, those are the participants in the execution, which depending on whether the transaction proceeds or not, will update their locally stored data. We have two rounds of communication in this protocol. In order to do recovery after a crash, each of the participating sites maintains a local log that is stored persistently on hard disk. So this is how it looks like. This is relatively a simple explanation of the protocol, omitting some details, but showing you the high-level picture. We have the coordinator and one or multiple subordinates. In the first phase of communication, the coordinator essentially tries to find out whether the transaction should commit or abort. And whether that happens may depend on data that is available on one of the subordinate nodes. So the coordinator essentially needs to ask them whether we should proceed with the transaction or not. So the coordinator sends essentially a question to the subordinates whether they want to proceed or not. Then each subordinate makes a decision based on the data that is locally available to it and replays back to the coordinator. Now the coordinator only decides to proceed if it hears back with a positive reply from all of the subordinates. If that happens, it informs all the subordinates in a second round of communication that we will proceed with executing the transaction. So they should adopt the changes to the local data that come with the transaction. And then finally, the subordinates acknowledge execution to the coordinator. And at that point, the coordinator knows that the transaction execution has finished. So this is the two-phase commit protocol. So In order to be able to recover from failures from some of those participants, every one of them maintains a log locally where before sending a message, we essentially log the current state persistently. And if one of those nodes fails and comes back online later, we can analyze that log in order to determine exactly at which phase of the protocol we failed. In order to recognize that other nodes failed, we typically use a timeout. So if a node doesn't hear back until the timeout from one of the other participants, then we assume by default that the other participant has failed. So this is how we detect that other participants or the communication with them has failed. Now here we can think about what happens if we fail in different phases of the protocol and on different nodes. For instance, if in the first phase, one of the subordinates fails before it can reply to the coordinator, then we know that the coordinator will wait until the timeout for the subordinate to reply. And if that doesn't happen, then by default, we assume an abort. So here, the subordinate, if it sees that it has failed before sending back a reply to the coordinator, the subordinate knows that the transaction must have been aborted. And also, if the coordinator fails in the first phase, then we will also assume an abort of the transaction by default. For the second phase, if one of the subordinates fails after sending out the reply in the first phase, if that subordinate has sent back a no decision, then it knows that the transaction was globally aborted because we can only proceed with the transaction if all of the subordinates agree. If the subordinate failed after sending a positive reply back to the coordinator, it is possible that the coordinator has decided to proceed with the transaction. So in that case, the subordinate would have to query the coordinator in order to find out whether the transaction should proceed or not. And if the coordinator fails in the second phase, then we can simply use its log entries in order to see whether the global decision was to proceed with the transaction or whether to abort it. I believe there was a question in the chat. Yes, very good. Yes, exactly. So the participants here are writing persistent log entries before sending out their messages. This is what allows us to recover things later if necessary. All right. So this was our little overview of distributed database management systems. Is there any questions about that material for the moment? All right, and here there is one question about what happens if one of the subordinates fails in phase 2 after sending a yes. So in that case, the subordinate needs to know whether the global decision for the transaction was to proceed or whether to abort it. It depends on what the other subordinates have replied. In order to find that out, the subordinate needs to contact the coordinator. It has stored the address or the identity of the coordinator in the persistent log. So after the subordinate wakes up again, it will look up the address of the coordinator and then send a request in order to find out whether this current transaction has finally aborted or committed. And if it is committed, then it will do the local changes that the transaction implies. Otherwise, it will abort the transaction. So it doesn't, strictly speaking, doesn't restart the transaction locally, but essentially it asks the coordinator whether it should apply the local changes to the data that come with the transaction, knowing that the other subordinates of that transaction will have done the same with their local data. Does that make sense? All right. So now we're going to discuss about a different class of systems which implement something called eventual consistency. The material that we will discuss here is not in the book, but you can read up in more detail in the papers that you see here, which is the papers in which the systems that we will discuss in the following have been initially described. Now in the following, we're going to talk a lot about consistency, and I want to start with a little terminology warning, because we have already heard about consistency, which was the C in the ACID transactions. And in that context, consistency generally means that your data is consistent with all constraints. Now, in this lecture, we will be discussing about systems and about insights that come from a little bit of a different community. Therefore, the terminology is slightly different. And if in the following I talk about consistency here, what I mean is that in a distributed system, the different replicas appear to be in sync. So meaning that if you have an update to an object and you read the object later, then you will always see the updated value, and guaranteeing that is actually very difficult if for each object you may have multiple copies distributed over different nodes in your system. So the consistency that we will discuss in the following is a little bit different from the consistency that we have been discussing before, which is a bit unfortunate, but here there's just terminologies from different communities that overlap a little bit. All right. So let's discuss a little bit about trade-offs in distributed data systems. So we have discussed about consistency in the sense that different copies of your data appear to be in sync. And in the following, we're going to see a little example that shows that consistency can sometimes conflict with availability, meaning the capability of a system to answer requests. So let's assume that we are considering an online shop which has multiple sites in order to serve customers in different regions, for instance. Here in the simple example, we only have 2 sites, and each of those sites has a copy of the inventory, meaning how many items you have left from each type. And of course, those sites need to communicate with each other. So if one of them receives a request, they can update the other one in order to make sure that those inventories are in sync. Now let's assume that there is a communication failure. So here the network gets partitioned, we say, meaning that the different parts of our system cannot communicate with each other anymore. And now let's assume that there comes a customer who wants to buy something. So here, let's say somebody wants to buy a specific DVD. Now we have a couple of possibilities to handle that. Now, the first possibility is that we accept the request, which means that in our site1 directory, we have to reduce the DVD stock by 1. But that means that our 2 copies of the inventory now become inconsistent, because at this point in time, we cannot communicate that change to the other side because communication is interrupted. Now, the other possibility is that we just say, we are not available, we cannot treat this request, because if we did, our inventory could become inconsistent. And at least in principle, that could cause problems. I mean, imagine, for instance, that both of those sites start accepting buy requests for DVDs independently, and then at some point you have sold more DVDs than you actually have. So there could be problems, but of course here we would make the customer unhappy, and we would lose one sale. Now, this little example shows you that is a trade-off sometimes between being consistent between different data copies and it being available, meaning being able to answer requests. And this example essentially has been generalized into something called the CAP Theorem, which abbreviates a consistency, availability, and partition tolerance, and essentially claims that it is an intrinsic trade-off between those different things. I mean, all of those are things that you want. You want to be consistent, you want to be available, you also want to tolerate network failures, where your system gets partitioned into different parts that cannot communicate with each other. But this theorem essentially says that you cannot always have all of those together. So with some little extension of the example that we have seen before, essentially the authors make the case that you cannot have the intersection of all 3, which is what you ideally want. Now, among the remaining options, traditional database management systems, they would typically prioritize consistency above everything else. So this is where traditional database management systems are located, at the intersection between consistency and partition tolerance. On the other side, the type of systems that we will be discussing about today, those are called NoSQL systems, which favor availability over consistency and would rather decide to sell the DVD even if they cannot currently communicate with the other copies of the inventory in the example from before. So those are 2 different trade-offs, and it depends on the specific scenario which of them you want to make. Now, the class of systems that we will be discussing today provide something called eventual consistency. Eventual consistency essentially means that we don't absolutely require our data to be consistent at all times. But instead of that, what we try to achieve is that we at least become eventually consistent. So if there's no new updates to the system, then at some point, all the copies of our data will become consistent again. So this class of system is motivated by application scenarios such as online shopping, because here you absolutely want to make sure that you can serve your customers as much as possible, because if you don't, then you lose money. So in those scenarios, perhaps being always available for customers can be even more important than having your data consistent at all times. The paradigm is also called base, which differs from ACID already in terms of semantics. So base stands for basically available, soft state, and eventually consistent. So here basically available means that you prioritize being available above everything else. Soft state means that you don't necessarily require your data at different sites to be consistent at all times, and eventually consistent means that eventually you will converge back into a consistent state. So that is kind of a counter, this is kind of the complement of ACID transactions in a way. And this is what those NoSQL systems that we will be discussing are aiming for. NoSQL is actually a bit of a broader term. It has been used with multiple semantics. In general, it designates systems that make a little bit different design choices compared to traditional relational database management systems, which could, for instance, mean having reduced the consistency base. Could also mean that we support different languages than SQL. In many cases, simplifications of SQL, which makes it easier to support them efficiently. It also refers to systems that use different data models compared to relational database management systems. So the term has multiple different semantics, but here in the following, we're gonna particularly focus on the reduced consistency requirements compared to traditional distributed database management systems. Now in the following, we're going to discuss about a couple of representatives of that category of systems, starting with Apache Cassandra. Now, Apache Cassandra is a distributed system. All of the nodes in that system, they have the same role, which means in particular that there is no single point of failure. If one node goes down, then the other nodes, they can continue operating. It is a so-called wide column store, which essentially means it looks a bit like tables in the database, with the difference that different rows in those tables, they can have a different number of columns. So in a way, this is more flexible than the traditional relational data model, where each table needs to have rows that each have the same number of columns. It supports a language called CQL, or Cassandra Query Language, which in a way is a simplification of SQL, because, for instance, you cannot do things such as joins, which makes it also easier to support it efficiently. It is optimized for scaling up linearly when adding new nodes. So basically, if you add more nodes, then you always increase the number of requests that you can answer. And that is a very desirable property to have for a system. And it offers you various ways in order to tune trade-offs between consistency and availability, as we will see in the following. So the way in which we achieve eventual consistency in Apache Cassandra is by gossiping. And gossiping essentially means that those different nodes in the system, every once in a while, they will exchange information about new updates. So any new update will eventually propagate to all the nodes in the system. So here, for instance, we have those sites and there is an update at one of them. Then at some point, this site will communicate with one of its peers here and propagate information about the update. Then at some later point, this site will communicate with its peers as well and propagate the update until finally the update has reached all of the nodes in the system. So this is how we propagate updates eventually over the entire system. But you also see that for a certain amount of time, the different copies of your database might be inconsistent. Now, this is essentially what I illustrated with that little example. The way in which we achieve eventual consistency is by periodically exchanging information between those nodes. each of the nodes only communicates with a limited number of peer nodes in order to keep the overheads reasonable. And if we do that, then eventually updates will propagate throughout the entire system. There's one subtle detail about object deletions that might be worth quickly discussing. Question to you: does anyone see any reason why deletions might be problematic in this context? If we get a deletion request at some node, we could simply delete the corresponding object from our database. Maybe tell other nodes that it was deleted. So all the nodes that are currently online will delete the object from the database. Is there any possible problem with that? If you think about one node which might not have been online when the delete propagated through the system, and then a little bit later that node which still has the object stored comes back online. Does anyone see why that might be problematic? Right. Very good, very good. In that situation, there's the right answer in the chat. In that situation, if the node which still has the object stored that was deleted at the other nodes, if it comes back online, then it has missed the delete, and therefore it might actually think that it knows about a new object that the other nodes don't have stored yet. So it will potentially try to propagate information about this new object to the other nodes, and then the object that was previously deleted might in principle get inserted again. So that is the problem with simply deleting objects from the database. And in order to get around that, what Cassandra does is when it receives the request to delete an object, it doesn't completely throw out that object from the database, but it essentially maps it to a so-called tombstone symbol, which keeps track that there was an object, but that this object was deleted. And because we know that, we avoid the situation that I have described before. We always keep track of which objects have already been deleted. All right. Now, Cassandra allows you to tune consistency in various ways, actually. You can tune, for instance, the number of replicas that you create from each object, which, of course, the more copies you create, the safer you are against certain types of failures. You can also tune the number of replicas that need to be read for a read to be considered successful. And equally, you can tune the number of replicas that need to be written for a write to be successful. So for instance, let's say that we have 10 replicas in our system from every object. And we could say that in order to consider an update to the object as a success, we require the system to update at least 3 out of those 10 replicas first. On the other side, if you have a system which might have slightly different versions of an object at different nodes, then it might be useful to read not only one copy, but to read multiple copies, and then use something like timestamps, for instance, in order to identify the most recent version among the ones that you have read. So here you could also decide that in order to consider a read a success, we need to read at least, let's say, 5 out of those 10 replicas, and then the chances should be pretty good that at least one of those 5 is the most up-to-date version. Now, if you consider those parameters, the replication factor, the number of reads, the number of writes, what must hold on those parameters in order to guarantee strong consistency, meaning non-eventual, but in order to guarantee that you essentially, after updating the object, if you read it again, you will receive the most recent version. Okay, good propositions here. Okay, there's the proposition to set the number of replicas, the replication factor, to the number of writes, which essentially means that in order to consider a write a success, I have to update all of the replicas in my system. So that is absolutely correct. Yes, if you would require that, then you would guarantee a strong consistency. Of course, it means that you would not be available if at least one of your nodes has currently failed. So it is relatively restrictive. This proposition is absolutely correct, but there's a couple of other possibilities to ensure the same thing. Okay, and so here I see a generalization of that formula. Okay, the number of writes plus the number of reads should be greater or equal to replication factor plus 1. Okay, very good. Yes. So that is exactly the more general formula, which also includes the case n equals w as a special case. Very good. So if you have this relationship between different parameters, then you guarantee strong consistency. Now let's see a couple of examples in order to see why that makes sense. So here we have again those 6 sites, and here, for instance, we set the replication factor to 6. We have 6 sites. We set the number of required reads to 2 and the number of required writes to 1. So if we have one update, we might, for instance, apply it only to site 2. And if we read 2 of those replicas, it might turn out that we read site 6 and site 5. And in that case, none of those reads covers the updated version. So we would read an outdated version of the object. On the other side, we might get lucky here and read site 6, but also site 2. And site 2 is the one that was updated. So in this case, we are lucky and receive the most up-to-date version of the object. So with the current settings for replication factor, reads and writes, in some cases we get the most recent version. In other cases, we don't get the most recent version. Now, for instance, we could choose R equals 3 and W equals 3. So we require reading 3 replicas for each read, and we require writing 3 replicas for each write. And as you see here with 6 replicas, we might still run into the situation that we update some subset of replicas and later we read the other replicas. And since there's no overlap, we don't read any replica that was already updated. Again, here we would we might get an outdated object version if we have a read directly after a write. So here we assume that the nodes have not yet had the chance to gossip among each other, which happens if the read follows sufficiently quickly after the write. Okay, so even with the current parameter settings, there's still a case where we might read outdated values. But if we increase the number of required reads to 4, in that case, there's no way of setting this up in a way that we don't read at least one replica with the most current version of the object. And this is why setting R plus a W greater N guarantees a strong consistency. You have the outline that summarizes what I just said. So if this formula here holds, then we can guarantee a strong consistency, because whenever we read replicas, we are sure that we read at least one replica with the most up-to-date version. Is there any questions on this currently? All right. So that was Apache Cassandra, one first eventually consistent system. And now we're going to see a second representative, which is the Amazon Dynamo system. And that system was specifically developed for the requirements of Amazon for their web shop. For instance, it tries to be always writable, because each write to your data corresponds to a sale. And if we lose writes, then we lose sales, so we lose money. So we absolutely don't want this to happen. So the system tries to be very accepting about write operations. And it also uses, for instance, a couple of customized conflict resolution strategies. So as discussed, the first property of the system is that we want to be always writable. And that essentially means that we want to require only a few updates to replicas in the system before we consider a write operation a success. Even if only, let's say, one single replica is available, you might still decide to accept updates to that replica and propagate those changes later to the other ones. And that means, of course, that our data might be temporarily inconsistent, but as Apache Cassandra, Amazon Dynamo also aims to be only eventually consistent, so that is okay. Since we have temporarily inconsistent data, it means that when reading objects, you might actually get multiple different versions of an object. And in order to merge those conflicting reads together, Amazon Dynamo applies two strategies. First of all, it tries to identify and discard outdated versions, if it can do so in a generic manner. If that doesn't work, it uses some customized reconciliation strategies. So that is one of the reasons why I selected the Amazon Dynamo system, because it deals with an issue that is typical for eventually consistent systems, which is that you might get multiple conflicting versions of an object, and then you have to decide how to make sense of that and which one of them to discard, or how to merge together those conflicting versions. Now, the first thing that this system does is it tries to identify versions that are clearly outdated. And in order to identify those versions, it uses something called vector clocks. Now, a vector clock is associated with the version of an object, and it essentially keeps track of one counter for each node in the system. So that keeps track essentially at which point the object version was updated by which node in your system. So whenever a node updates an object version, it increases its local counter and then timestamps the new version with the updated counter. And you have one of those counters for each component in the system associated with each object version. And that allows you to track which version has been generated from which other version, because if the counters of one version are uniformly lower than the counters of another version, it means that the other version was created based on the previous version. So this allows you to essentially keep track of the version graph, you would call it in certain systems, which essentially tells you which version was generated from which other version. And if you have if your read returns 2 versions, and for one of them, the vector clock is uniformly more advanced than for a second one, then you can discard the second one because you know that all the updates which are part of this second one have already been integrated in the first one. So this is how vector clocks are used, and they allow you to discard some subset of those object versions that you get returned by the read. Here there is a little example of that taken from the paper. You can read up more details in the paper if you're interested. You have the reference at the bottom of the slide. So in this example, we have 3 servers, SX, SY, and SZ. And here we are updating an object. In the case of Amazon, that could, for instance, be a shopping cart. So here, the first update to the object is handled by server SX. There's a question about this in the chat. I'm quickly going to go over this example, and then I'm going to look at the question. So here, first of all, the object is updated by server SX, and so we get the version D1 of the object, and associate the vector clock SX1 with it, which means that server SX has integrated one update. The other servers are currently omitted because they don't have contributed any updates. Now let's say there is another object, another update to the object, which is also handled by the same server SX. So we get the version D2 of the object, and our counter for SX increases. So we get the vector clock SX to 2. So here we have already 2 different versions of the object, but clearly the second version of the object is the more recent one because it has been created based on the first version. And here we see that SX is set to 2, while it is set to 1 in the other version. So here the vector clock of D2 is uniformly more advanced than the vector clock of D1. Now let's say that the version D2 is updated in one way by server SY and in a different way by server SZ. So now we have 2 diverging versions, D3 and D4. And as you see here in the associated vector clocks, both of them have SX, the counter SX set to 2. D3 has the counter SY set to 1, while D4 has the counter SZ set to 1. So the counters that are not shown are implicitly all set to 0. And in this case, it actually becomes difficult to reconcile those 2 diverging versions, because now we cannot really say that any of them is uniformly more advanced than the other one, because one of them includes changes by SY, while the other one includes changes by SZ. So in this case, we have to somehow use, for instance, a domain-specific reconciliation strategy in order to get back to a common version. And that common version now would have the vector clock that essentially integrates the changes by SY and SZ. And here we have one additional change by SX. So this is the way in which we use those vector clocks in order to compare different versions. And I think, yes, the question was resolved. Okay, good. So now let's see how we can reconcile diverging versions of an object. And here the Amazon Dynamo system advocates a domain-specific resolution strategies. For instance, here is how the shopping carts are merged. This is taken from the paper. A typical example of a collapse operation is merging different versions of a customer shopping cart. Using this reconciliation mechanism, an add to cart operation is never lost. However, deleted items can resurface. So here you can use domain-specific strategies which are aligned with your business goals, which of course is to rather sell more items than less items. And therefore, when merging shopping carts, then you will rather find that you will discover more items than you initially intended, but typically you won't find less items than you initially intended. And that is caused by this customized reconciliation strategy. So this was the Amazon Dynamo system. As the Cassandra system, it implements eventual consistency. And here I have put a couple of different consistency guarantees on this slide. This list is not exhaustive. There's lots of different consistency models and associated systems. Here I just outlined some of them. In general, when people talk about strong consistency, then this is essentially that if you updated an object in your system and later read it, you will get back the most recent version. Weak consistency is kind of the opposite of that, and eventual consistency is one special variant of general weak consistency. To give you some examples for what other consistency models are around there, there's, for instance, something called read your write consistency. And that means that one specific process, which is updating objects, will always read its own writes, at least, but when comparing different processes, that might not necessarily be the case. There's also a specialization called session consistency, which is essentially read your writes consistency within the specific context of one session. There's also a property called a monotonic read consistency, and that essentially means that once you have seen the most recent value once, you will never see an older version when reading more. So those are some consistency properties, but there is many others. Now, in the following, we are approaching the end of the time limit. Perhaps one quick example about how eventual consistency manifests in practice. Here I'm gonna show a couple of experimental results of a paper that evaluated another eventually consistent system, which is Amazon's SimpleDB. And in this experiment that you see here, what they did was essentially they update an object and then they read it immediately afterwards. On the x-axis here, you see the amount of time that passes between the write and between the read operation. And on the y-axis, you see the probability to read the most recent value. And as you see here, after about 500 milliseconds, there is a jump from about probability 33% to probability 100%. Does anyone have a suggestion about how the underlying system could be set up? So this is a system where we don't necessarily have the details about how it is working internally, because this is not necessarily released by Amazon, but by doing those experiments, you can come to some assumptions about how the system is working internally. And if you see this, so after 500 milliseconds, our probability to read the most recent value jumps from 1/3 to 1. What do you make of that? What do you think what the system is looking like? Okay, very good. Yeah, so after half a second, the central coordinator looks for the most updated version and sends updates to all nodes. Okay. If possible, we might want to avoid the central coordinator. But okay, so in general, after half a second, it seems that updates are propagated. It could also be like different nodes talk to each other every half a second. Okay. If you would have to guess how many replicas there are in the system, do you have any suggestions? Okay, very good. Yes, it could be 3 replicas, right? So what this could mean is that there's 3 replicas in the system, and we have to update one of them only in order for write to succeed. And we also only have to read one of them for read to succeed. So in this case, we could assume that we have those 3 replicas. If we read them immediately after the write, then we have a chance of 1 to 3 to get the right replica, which already has the most up-to-date version. And then every half second or so, those different replicas synchronize, so your update is propagated to others. So that would be one reasonable assumption in line with those experimental results that we see here. And more generally, those experimental results give you some intuition for how quickly those things propagate in practice. So we have talked about the theoretical concept of eventual consistency, but this tells you something about how eventual that is in practice. And here it seems that changes propagate already fairly quickly. We also measured, for instance, the peak times between writing and until the write is received in following reads. And at least for the 99% quantile, that works pretty well. And we have a very stable times around 500 milliseconds. There's a couple of longer peaks, but they are fortunately quite rare, but they might still occur. So with eventual consistency, you can never be 100% sure. Every once in a while, it might actually take significantly longer to propagate your updates, up to a couple of seconds, basically. And they also measured how often it happens that we read stale, meaning outdated values after reading fresh values. Here's the percentage table. And since that one is non-zero probability, it means, for instance, that we don't have this non-monotone reads property that I quickly mentioned before. So this was an overview of eventually consistent systems. We have seen multiple representatives of them. We have discussed about a couple of key issues, and now I have also shown some experimental results to give you an impression for how that works in practice. The next time, we're going to see yet another category of systems, which is a little bit more recent and tries to make even stronger guarantees than traditional database management systems. Have a nice day, and then I see you again on Friday.